electrons that we have will help us to determine how that particular element is going to behave, or the atoms of that particular element is going to behave. So if you look at the electron distributions, for lithium, it's 1s2, 2s1. Lithium number 3. You have total of 3 electrons there. According to the electron distribution rules there, you can put the first 2 electrons in the 1s orbital, and you can only put 2 electrons on the n equals 1 level. The third electron will have to go to 2s1. Sodium, 1s2, 2s2, 2p6, 3s1. Okay. Potassium, we can have 1s2 all the way to 3p6, and we'll have 4s1. Okay. So here, the group 1A elements, you have 1 electron on the outermost shell. You have 1 valence electron. Only the valence electron can participate in chemical reaction. Well, this is why we put lithium, sodium, potassium in the same column, because they have the same number of valence electrons, 1. Okay. The one electron is on the 2s level, 2s orbital for lithium, but it's on the 3s orbital for sodium, 4s orbital for potassium. Okay, so but they all have the same number of valence electrons. And only, remember, only the valence electron can participate in chemical reaction. Okay, so the correlation between the core electron, valence electron, and the number of periods, and the periods and the group numbers there is that core electrons are located in the inner shell, and valence electrons are the outermost electrons. And valence electrons determines the chemical property. And the number of valence electrons equals to the group number. That is only the case for main group elements, group 1A through 8A. So if you have 7 valence electrons, that belongs to group 7A. If you have 1 valence electron, that's group 1A. Okay? And again, remember, this is for main group elements only. In transition metal, sometimes there is a correlation, sometimes there is not. So there is no, you cannot generalize that for transition metal elements there. But for main group elements there, the number of valence electron equals to the group number. The key word is the valence electron. Number of valence electron equals to the group number. Okay? If you have group 6A elements, well, they have 6 valence electrons. Knowing that, if you look at, well, we can ask you this question. Which group in the periodic table has the outermost shell or valence shell configuration of ns2 and p4? Well, N stands for the different energy level, n equals 1, 2, 3, 4. Okay? So the total number of valence electron though is 2 here, 4 here, total of 6. For main group elements, 6 valence electrons means group 6A. So group 6A means this particular column. Every single element in this column will have the same valence shell electron configuration. For oxygen, it's 2s2, 2p4. For sulfur, it's 3s2, 3p4, so on and so forth. Every time you go up to the next period, the n number increases by 1. But the number of electrons stays the same on those 2 sublevels, ns2 and p4. Okay, so what we're trying to get here is that we're trying to understand how the electrons are being distributed, because that's what determines the chemical properties of those atoms there. Okay, so another question there, we ask you to identify the group number and for the elements indicated in this particular column. Well, this is group 6A. Okay, well, similar, very much similar to the other side of the coin, if you will. And group 6A, the valence electron configuration will be ns2 and p4. 4 plus 2 equals to 6. N depends on which period they're in. N equals to 2 here, 3, 4, 5, 6. Okay, and so on and so forth. But they have the same valence electron configuration. 4 on the p orbital, 2 on the s orbital. Total of 6 electrons. Okay. Another type of question there, combining what we talked about the quantum number. What label is given to an orbital with a quantum number n equals to 4, L equal to 1? Well, something that I say I need you to memorize. When L equal to 0, it corresponds to the s orbital. L equal to 1, it corresponds to the p orbital. So when n equals to 4, L equal to 1, we're talking about this orbital, 4p orbital. So the number 4 corresponds to the principal quantum number. And then p, the letter p, corresponds to L equal to 1. How about n equals to 4, L equal to 2? That will be your 4 SP, what's the next, D orbital. How about n equals to 4, L equal to 3? 4F. That's what we need you to be able to determine. Okay. So combining the quantum number and the destination there, we need you to be able to identify the exact orbital that we're talking about. What about this type of question? What's the maximum number of electrons that can occupy n equals to 2? Total of 8, 2n squared. Okay. Now, what we're trying to get to is to understand the electron distribution. And we also need to know how much total number of electrons that we can have on each n level. Okay, so these are the questions that we need you to be able to answer. And then, in this case, in 2n squared, that relationship is something that you need to remember. Right? And then, here's another question related to that SPDF block destination. Which element is an S block element? Well, to answer this question, you have to memorize where is the S block in the periodic table, where is the D block and F block and all that. So looking at the periodic table, this is something that will be given to you. Okay? If you look at all the elements in here, cesium is in group 1A. Everything else is pretty much on this side. The first two columns is your S block plus the helium. Okay? So the answer would be cesium is going to be your S block element. I can give you a list of different elements there, and I'll ask you the question, which one is the D block element? You have to be able to identify this is the D block. Whatever is the false in this region is going to be D block element. Which one is the P block element? You have to be able to identify this is the P block. So that picture that I showed you earlier, SPDF block destination, that's something that I do need you to memorize. Okay? And the SPDF block destination has something to do with the number of electrons there. 1s, well, with group 1A, you only have 1 valence